Okay, so let's begin. We'll begin with the doubt sheets. So the first doubt sheet actually is useful if they were more in number. They said, I felt the class went a little fast, and after the class got over, I asked the remaining few students who were there. One of them said this was the slowest class. So I don't know. So if more of you feel that it's going fast, just let me know. That will help me to modulate, right? But if 1 out of 70 says it's slow, I don't know if it's noise or not. There were a couple of questions about this non-circular contours. It's not clear, does this perpendicular depend on the initial position, or is it true all the time for non-circular contours? If it is true for every initial point, is it only for exact line search? So as we showed in the proof, it is true when I did exact line search. When I did exact line search, every step was perpendicular to the previous. That just came out of simple algebra, right? It does not depend on the initial position, except if somehow you got lucky and the first starting point brought you straight to the solution, right? In case your initial direction was pointing straight at the solution and the gradient, the function value is always going reducing, then you will reach in one shot. In that case, we don't have to talk about perpendicularity between steps because there is no step, there is only one step. But I take any other point, this is a property of gradient descent, that the steps are always orthogonal to each other. Okay. Just like the tricks mentioned for proving the Zoutendic condition, can you suggest common tricks used in bounds of different norms? I think one of the most common tricks is triangle inequality, Cauchy-Schwarz inequality. These are the other tricks which are used. Again, with the elliptical contours, was your implication that apart from that one point which gave a single descent direction, every other starting point will give descent directions perpendicular to previous steps? Yes, it does. Okay, then there is weightage of the different components of the course. I'll post it on the class website. Right, so we'll continue our discussion of the convergence of the steepest descent, gradient descent, or any descent method in general. Remember, the proof that we gave for convergence did not rely on gradient pk being a gradient descent direction. Pk just had to be what? Legitimate descent direction, and that's all that was required. So it's applicable to a broader family. Now, we proved that convergence happens. What we haven't figured out yet is at what rate does convergence happen, right? So this discussion is going to be about the rate. Now, as it turns out, this rate analysis, it's a little bit more tricky to do. So I'll make some simplifying assumptions, and with that simplifying assumption, we'll arrive at a certain rate. And then I'll point you to some other resources where people have worked it out in a more general case. It's much longer, the proof. So we'll prove it for a simple case. And that simple case is assuming the objective function to be convex and quadratic. Okay. So for simplicity, CF is cost function is convex and quadratic. Okay. One of the advantages of having a quadratic cost function is that I can actually do line search exactly. Okay, this is I believe one of the tutorial questions as well. Okay, so I can do exact line search is possible. It's a simple matter of calculus to show this. Exact line search means I actually have a closed form expression for the step length. So that's great because it helps me with the analysis. I don't have to do backtracking line search. I don't have to check for Wolf conditions. I can just get an expression at each k. This is the step length, walk along it. Okay. Remember, what was the definition of exact line search? How did I define exact line search? Right, rate d phi by d alpha is equal to 0, right, at alpha equal to alpha k. That is the meaning. I can't do any better than this step length, given what? What is assumed fixed over here? What am I assuming fixed over here? The direction. Pk is fixed. So I've been given the descent direction and I cannot change that. I'm going along that. What is the best I could do? It's alpha k. Okay. Let's just note that over here. Given Pk. Okay. So here is my cost function. So I want it to be convex and quadratic. We've already seen a quadratic form before, right? So this is the form of a quadratic cost function. Are there any constraints on Q? For it to be convex, it's already quadratic because there's x multiplied by x. For it to be convex, do I need something else? Q should be positive definite. Obviously, it's also symmetric and it's positive definite. And remember the geometric intuition for that. If it is not positive definite, I don't have a upward opening cup. I can have maybe a downward cup, I can have a saddle point, in which case it's meaningless to optimize a function that is unbounded from below. So this is guaranteeing me that it's at least a sensible thing to optimize. Right. Okay. So this was our expression. What is, so now to do calculus with this, the things I will need is grad f is what is going to be needed. That's going to be used everywhere. So we have derived this in great detail. What is grad f in this case? First term I can do by product rule. What will I get? Q plus Q transpose and multiplied by, whole thing multiplied by x. It's symmetric. Q plus Q transpose will give me 2 times Q, right? And half cancels off. I am left with Qx minus B transpose. Okay. Oh, sorry. B transpose. Okay. So this is, let's call this 1, this is 2, okay. I'm going to, for this proof, I'm going to assume that we are doing steepest descent, okay. Not any general descent direction, we'll assume steepest descent. So let's know that. Assume Pk equal to minus grad f. Okay. This is it. So our old friend phi of alpha, how did I define phi of alpha? So it's f of x k plus 1, f of x k plus 1, which is, if I write it in terms of xk plus alpha k pk, but pk is already assumed to be negative grad. So minus alpha k grad f k. Okay. Now, exact line search implies that phi dash alpha equal to 0, right? And you can see that I already have in the past computed phi dash alpha using which rule? Chain rule, right? Can someone remind me what was the expression for phi dash alpha? Grad of f of xk plus 1 transpose multiplied by pk, right? Which is going to be negative grad, let's call this fk plus 1 transpose grad fk. Is that right? This is just simple substitution. This is what phi dash alpha is going to give me. Yeah. You can see that this is going to be, is this an expression of a scalar, a vector, or a matrix? It's a scalar. It's an inner product of 2 vectors, and that's what I expect because phi is a function of a single variable and outputs a single variable, so everything is fine, right? Now, if you assume exact line search which gives you this, we can actually get a closed form expression for alpha, which we will derive in the tutorial. So let's assume it for now. I'll give you the final result. So I will be able to write my xk plus 1 in terms of xk and this expression for alpha. So quite a simple derivation. Now when we talk about convergence, okay, so this is just sort of building up all the nuts and bolts needed. Let's get back to what we wanted to talk about. We wanted to talk about convergence. Now convergence means the distance between what and what are we interested in? Is it that or is it the solution? We just look back at the definition of convergence. Is it the difference between iterates or is the difference between the iterate and the true solution? The stationary point. Between iterates. The convergence points, right? So, I mean that kind of makes sense. When I'm talking about convergence, I'm interested in something like where x star is the, what is x star? Stationary point. This is what I'm interested in, right? When I say convergence rate means how quickly am I arriving at the solution. This is finally what I'm interested in, okay? And typically the way it is defined is with the 2 norm. That's the definition that we had seen, okay? So as it turns out, if I were to use the 2 norm, the math gets quite grungy, okay? Already, I mean, this is not a very easy proof to do, and if I insist on 2 norm, the proof gets difficult. However, as you've seen in the tutorial, there are ways to relate one norm to another norm via inequalities. So if you can prove something for one norm, it will kind of hold true for another norm as well. So there is, instead of using the 2 norm, we'll make our life easier and work with a norm that is more appropriate for this problem. So I'm going to give you an unusual definition of a norm and you tell me whether it makes sense. Question? This equation for xk plus 1? Yeah.
Like that constant term which you're using for scaling.
You mean the alpha k?
That alpha k.
How did it come?
Like the gradient f at k plus 1 we don't know. Without alpha we don't know what xk plus 1.
Oh yeah. He caught it very well. There's actually a typo. I was looking at this expression and then I just jotted it down. It's actually not there. I can't know fk plus 1 in future, right? So it's only based on the current iterate. Yeah, so you can correct that. Okay, so I'm going to give you a definition of a norm that, let's see, is it a norm? Okay, so I'm going to define in the following way, right? So this is going to be, I'm going to square it, A transpose QA. Is this a legitimate norm? Q is the same Q from before, not some new Q. Q is positive definite. Obviously symmetric also. So what are the qualities of a norm? Norm of x equal to 0 only when x equal to 0. This Q is positive definite, not positive semi-definite. That means all the eigenvalues or singular values, whichever way you want to look at it, are positive, right? So when can this expression go to 0? Only when A is identically 0. So the first property of a norm is checked. Is this quantity always positive? This is always positive, right? So what is the third property that we need to check for a norm? Triangle inequality, right? And we won't work it out now, but for a positive definite matrix, this also gets satisfied. So this is actually a norm. So long back we used to think of norm as simply the way the crow flies, right? L2 norm. But you can see that as you go into higher math, you can generalize the meaning of norm. Simplest extension is, when I walk along the curvature of the earth, it's not straight distance, right? It's Euclidean distance that I'm talking about. So this is one more generalization of a norm.